On the second exam item, we're given a cantilever beam and it has two different loads, a concentrated load here at point B and then a uniformly distributed load in the outer portion of it. And we're asked to find the transverse displacement that is out here on the free end. Right now, this is a fairly complex loading situation and not one that you're going to find in a beam table. That would, of course, be the first thing I'd look at, but it's not going to be there. And so I see a complex series of loads, and the primary concept I'm initially going to think about is how can I break the complex down into a series of parts and use then the principle of superposition, which just means to superimpose results together to get back to the whole. And in that case, let's just separate out the primary thing that's making this complex, and that's two different loads. So I have break one problem down into two, and now I've got a concentrated load at somewhere along the length of the cantilever, and then I've got a uniformly distributed load out at the end. Well, neither one of those is maybe necessarily terribly convenient, but what I can do from there is break this down further into the following, and that is, I think I know how to handle this one here all by itself, and then this one, well, I know I can look up in a beam table and have a situation where the uniform load is all the way across. Now that's extra load here at the left, so that I want to get rid of, and then handle it with this part here, subtracting off the effects there. So superposing those two will get me back to this one. Right? So that doesn't completely answer how you're going to find out all this stuff, because you're going to find this one in the beam table directly. Depending on the beam tables you have, you might find this one, but not in the one that we have with the textbook, and neither will you find directly this one. So how the heck is that really going to help us? Well, let's break that down and see how that might all play out. Let's take it one at a time. All right, so we'll take this cantilever one that says the concentrated load here. And now the key recognition is that the curvature is only happening over here in the left region. That's where we have the non-zero moment. That out here in the right-hand portion of the span, that has no load effects now. And so as this cantilever beam wants to displace, that outer portion is just going to go along for the free ride, and it'll rotate at whatever slope is happening right here at point B. All right, so that's a straight segment. So that means the displacement that I want, which is way out here at the end, is then going to be comprised of a portion that happens from the little cantilever beam portion that's only 8 foot long, right, with in effect the load out at its tip, plus then the rise over run version, which, remember, this is small angle theory, so tangent of theta is approximately equal to theta. So theta equals opposite over adjacent, which is the 4 foot, and I can then get that vertical drop, then is just 4 foot times theta b1. And these are two that then can be looked up for a cantilever beam that's only 8 foot long with a load out at the tip, and that's what you see right here. I've substituted in the 4 foot for this little piece right there, but the L1 is just this distance, that's the 8 foot. Substitute that into our expression, and I haven't put the value for P in yet. I'll do that in the next step. And you end up then, when you put P equal to 5 kips, that you have 896 over 3 P. And then that was, so I guess I did a little step in there, found the common denominator, etc. And then put in P equal to 5, and it's 4480 kip feet cubed over 3 EI. Got to keep track of the units. The kip comes from the load value, and the feet cubed came from that we had 8 feet cubed here, and then 4 feet times L1, or 8 feet squared, so kip feet cubed over here. And I'm not worrying about the minus sign right now. All the loads are going to make this beam curve downward, so I'm just going to show that that's going down there. Okay, now for step 2, or case 2 in our superposition model, that is the cantilever beam with a distributed load all the way across it, all the way out to its end. So that's a straight look up here, WL to the 4th over 8EI. We substitute in that we have 0.3 kips per foot, 300 pounds per foot, but 0.3 kips per foot times now 12 feet to the fourth will give us kip feet cubed, and divide by that 8, and we got 777.6 for that number, again acting downwards. Now for this last case here, where the distributed load is only from the fixed end over to some point, we're going to do the same thing we did up here. Find out what the displacement is at the end of that uniformly distributed load, and then that will be a part of what happens out here out at the real tip, and then plus the slope effect that we get. So same kind of thing that we had before, and you look up those equations again for what happens here at the tip. It's the same equation as before, but the L1 now becomes 8 foot for just here at point B, and then we got the 4 foot extension with that slope, that equation that we looked up from essentially from part 1 of our exam, and that gives you a value of the 256. Now as shown, that's acting downwards, right? And we're going to eventually need to subtract that to get that final displacement out here at the tip that we want, right? So there's your case 1 of the point load. There's your case 2 if the uniform load was all the way across the entire cantilever beam, and then subtract off this little last portion. And that's what you see going on here. You'll see that when I did the math initially, I made a mistake. I had the 4480 divided by 3 up here, but I forgot to carry that down. And so this number got to be much larger than I was expecting, and then it took me a little bit to go back and double check a few things and finally discover where I had made that numerical substitution error. But we do end up with 2015 kip foot cubed over EI, and it's acting downwards. The other thing I did was I used another technique called the moment area method to independently determine that that was exactly the correct number. There's some additional decimals out there. I think it's 2014.9 and change if you keep more around. But you'll eventually learn that 4 digits of accuracy in a displacement calculation in the beam is a little bit overboard to begin with. We don't know these loads that precisely. We're lucky if we know them to 1 digit, and we pretend like we have 3 digits of accuracy, but we really don't have that, because we're making projections about what those loads might be over the lifetime of the system.